Hey everyone, in this chapter we have talked about a new type of stereoisomers, which we called enantiomers. And enantiomers are molecules that are mirror images, but they're different from one another. And these enantiomers are the result of having what we call a chiral center. Right, so this is a carbon that has 4 different substituents on it. It makes that carbon asymmetric, meaning that it has no symmetry. And we can have 2 different forms of those chiral centers. And we learned last video how to label them or how to name them as either R or S. So in this video, what we're going to do is we're going to go beyond the situation of having a single chiral center, but we're going to look at some molecules that have more than one chiral center, and that's going to provide some different circumstances. We'll then get a little bit of practice on a type of problem where we just compare 2 different molecules and we decide what type of relationship that they have, whether they're constitutional isomers or whether they're enantiomers or whether there are a few new situations that we'll learn about now. So let's look at the situation where we have more than one chiral center. Alright, so I've chosen this molecule. This would be, what would we name this? It would be 1,2,3-chloro-2-butanol. Alright. So we have 2 chiral centers, one right here where the chlorine is because it has 4 different groups attached, and another one over here because it likewise has 4 different groups attached. So what we're going to do now is kind of go through a process of drawing all the possible combinations of chiral centers for this molecule and determine what the relationships are between them. I'm going to draw them tipped on their side just because that's going to make it easier for us. So I'm going to draw them down like this. Okay, there's our carbon skeleton. I'm going to draw the OH here, and I'm just going to arbitrarily choose for the OH to be a wedge, right? And so the H that's already also going to that position would be a dashed line. Let's put the chlorine with a wedge as well, and an H. Alright, so this could be, we could start somewhere else, but this is what I've chosen to do. Okay, so over in the upper right, I'm going to draw the mirror image of this molecule. Okay, so my carbon skeleton is going to go in the opposite direction like this. The OH is still going to be a wedge. Chlorine is going away, but still a wedge. And there's the H. Alright, so these 2 are mirror images of each other. Now down on the bottom, I'm going to draw another structure here. And what I'm going to do is I'm going to keep the OH the same, but I'm going to reverse the stereochemistry with chlorine. Okay, so I'm just going to put the H here and the chlorine like this. And then on the other side, I'm going to draw the mirror image of that. Alright, so when we draw mirror images, whenever there's a wedge, it'll stay a wedge. If there's a dashed line, it'll stay a dashed line. Okay, so these in fact are the 4 possible stereoisomers of 3-chloro-2-butanol. Alright, so now what we want to do is figure out what's the relationship between all of these different structures. Alright, so let's start up here. What's the relationship between these 2 molecules? Alright, well, we drew them as mirror images. Alright, so they're mirror images, and then the question is, will they be the same or will they be different? Okay, so these 2 are different, and so these compounds are enantiomers. right? They're stereoisomers that are mirror images. What about these two down here? All right, for these two, we also drew them as mirror images. And if we were going to flip one of these over, so rotate it around an axis like this to make the carbon chain fit the same way, the OH and the chlorine chiral centers would be backwards. Right? So these are also enantiomers, because they are stereoisomers that are mirror images. All right, what do you think about these two? All right, are those stereoisomers? Yes, because, right, this whole part is the same, but this part has a different stereochemistry. Right, so part of it's the same, part of it's different. Are they mirror images? No, these are not mirror images, so they're not enantiomers. They are stereoisomers, but we have to come up with a new name for this type of stereoisomer. So these are called diastereomers. Okay, and diastereomers are stereoisomers that are not mirror images. Okay, so if we have, we kind of have two possibilities here. Well, or three. The compounds could be the same. They could be mirror images as stereoisomers, or they're enantiomers, or they could be stereoisomers that are not mirror images, and then they would be diastereomers. Okay, so what about these two? All right, these also are diastereomers. And then we could look at these two relationships this way and this way. In both of these cases, these relationships are also diastereomers. All right, so if we have diastereomers with chiral centers, then what will be the case is that some of the chiral centers will be the same, but some will be different. To have enantiomers, they all have to be opposite. So we could confirm this by going through and determining the chiral centers for each one of these chiral centers, right? So if we want to do it for this one, we're going to rank these, number 1 for the alcohol, number 2 this way, 3 there. So we're going to go clockwise, number 4 is in back. So this is R. For this one, chlorine would go first. This carbon with the OH would go second, methyl third, 4 is in back, going clockwise. This also is R. All right? So when we make a mirror image, we just reverse them, and we can check that out too. We'd have again OH is 1. This carbon with the chlorine is 2, methyl is 3, 4 is in the back. We're going counterclockwise. So this would be S. Same with this one. Chlorine, number 1. Carbon with alcohol is 2, methyl is 3, 4 is in the back. Going counterclockwise. This is S. So when we have our two enantiomers, then notice that each chiral center is reversed. All right? So when we go from top to bottom here, when we go from this molecule to this one, notice this chiral center is the same as it was up there, and the bottom one has been reversed. We reversed 2 groups, so this goes to S. Right? And then when we do our mirror image, they're going to be the opposite. So this is S, and this is R. So we get RR, SS, SR, RS, all 4 possibilities. All right? So this also tells us that, or can give us a way to determine the possible number of stereoisomers. So the maximum number of stereoisomers is going to equal 2 to the nth, where the n is the number of chiral centers, or it could be just a stereochemical group. So we could also have cis-trans double bonds or something like that. So this is stereo groups. Alright, so in this case we have 2 chiral centers, 2 to the second power, 4, we have 4 stereoisomers. Okay? Alright, so let's make one more change and then we'll go through this process again. So what we're going to do, instead of having 2 groups here, the OH and the chlorine, we have 2 of the same group. So we have 2 alcohols. So let's go and let's just go through the same process. Okay, so here's our first one. I'm going to put the OHs both up. Alright, we'll make the mirror image over here. This one's a wedge. Okay, we'll go down below just like we did last time. We'll keep the first one the same, the first chiral center the same, and the other one will reverse. So we'll put the H here and the OH in back, and then we'll draw the mirror image of that compound. That, and then this one is just the mirror image again, like that. Okay, so what we now want to do is determine whether these molecules, or determine their relationships. So what about these two? What are their relationship? Okay, so we reverse the chiral centers. If we try to flip one over onto the other, they don't match, so these are enantiomers. Okay, what about these two? Alright, so let me try something here. So what I'm going to do in this case, so I'm going to take an axis that goes right through here, and I'm going to rotate the molecule on that axis. Okay, so what's going to happen is it's going to give us the carbon skeleton going this way, right? So this carbon here is going to rotate up to the top, be facing that way. So this OH has a dashed line. When we rotate it 180 degrees, it's going to end up with a wedged line, right? Because we've flipped this over. This is just like the spatula thing too, right, that we did before. So we flip that over, that chiral center is reversed, and then this position is going to swing down to the bottom. This OH was in front, so it'll be in back. This. Okay, those two are the same, so let's compare these. The OH is up in this one, it's up over here, it's back here, it's back here. Dang, look at that, these are actually the same. Right, so those aren't even, they're not even stereoisomers, they're just the same molecule. Okay, so why would that be? Right, so the reason is that these compounds are related by, well, these positions are related by symmetry. So one way that we can see this, okay, I'm going to go back up this way, and what I'm going to do in this case is I'm going to rotate around this center bond. Okay, so I'm going to keep the bottom carbon the same. I'm going to rotate this one around so this carbon is 180 degrees pointing the other way. So this OH is going to rotate 180 degrees. It's going to be a dashed line. This one's going to come out in front. Alright, so let's draw this side first. OH here, H here, alright, and then OH rotates to the other side here, H up in front, and notice that this molecule has a plane of symmetry right down the middle. Okay, so that means that it is achiral. And so it is the same as its mirror image. Okay? This situation here, where we have a molecule that has more than one chiral center, but it's achiral, this has a certain name. So here, so molecule with greater than one chiral center that is, oops, I'm going to run out of space here. It is achiral. Okay, we have a name for that. We call it meso. Okay, like the soup. All right. So meso is a property of a single molecule. So this molecule would be meso. All right, because it is the same as its mirror image. It's achiral, even though it has more than one chiral center. All right. So in this case, there's only 3 stereoisomers in that molecule. So we would calculate that there could be 4, right? 2 to the second power, but that's the maximum number. So we may have less. All right, so let's just review a few definitions here. Okay, so constitutional isomers. Constitutional isomers have the same formula, but they differ in the connectivity of the atoms. All right? Stereoisomers, right? They're going to be isomers too, so they still have the same formula. But they differ in the 3-dimensional orientation of the groups. Okay, there are 2 types of stereoisomers that we can have. Okay, so we're going to go kind of from here down to here and down to here. All right, so stereoisomers that are mirror images of one another are enantiomers. And essentially all the rest are called diastereomers. So these are stereoisomers that are not mirror images. Okay, most commonly we see diastereomers where we have more than one chiral center. Some will be the same, some will be different. All right? Molecules that have enantiomers will be chiral. Okay, so that means it's so they have a mirror image that's different. It has an enantiomer. It's different from its mirror image. Achiral is a molecule that is the same as its mirror image. Okay, meso is an example of an achiral molecule, but it's an achiral molecule that does have chiral centers. And it typically has to have more than one. Right? Other achiral molecules most commonly won't have any chiral centers, right? But you can have achiral molecules that have chiral centers, and those are called meso. All right? So let's different molecules and see if we can determine what relationships they have. Okay, so here's the possibilities. Okay, they could be the same, right? They could be constitutional isomers. They could be enantiomers, or they could be diastereomers. Okay, so these are our four possibilities. All right, so what about the first two? All right, these two are just the same, right? No chiral center. If we took this molecule and just rotated it up onto the other one, it would just superimpose right on the top. Okay? And part of it is that it has no chiral center. All right? What about the next two? Okay, these are also the same. Right? If we just, there's no chiral center, and if we just flipped one over, it would lay right on top of the other one. Okay? What about the next pair? All right, let's see if we can overlap them. So notice that the amine is on the opposite side, right? So if we took this molecule and flipped it over, so we're just going to take this and we're going to flip it over this way. We could redraw it. Right, we flip that over. The amine is going back here. It's going to be coming forward. The OH is in front. It's going to go back. Then we compare. Oh, look, that one's the same too. This is getting boring. They're all the same. All right, what about the next one? All right, so look, the carbon chains are oriented just the same, and so if we look at the chiral centers, right, the two bromines, so this bromine is opposite of that one, this one's opposite of that one. What about this position? That one, is that a chiral center? No, that's not even a chiral center, right, because there's two CH3 groups. We don't even have to pay attention to this one. So we notice that both of these are backwards, right? So what does that make them? These two are enantiomers. Okay? Alright, let's look at some even more complicated ones. Okay, so these are two sugars. In fact, this is this one over here, this is glucose, and this one is galactose. Alright, if you link those together, you get maltose, or milk sugar. Alright, so what's the relationship? Okay, so as we look through the molecules and compare them atom to atom, so look at this position. Chiral centers, same, same. This one OH down, same. This one, same. Oh, look, this one center is different. This one's the same. We have multiple chiral centers, but we have some that are different, some that are the same, and one that's different. So these are diastereomers. All right. What about the next one? All right. So let's see. Let's rotate one of these so we can overlap them. Okay. So I'm going to take an axis here and I'm going to rotate this one over. Right, and so I'm going to have the carbon chain going the other way. The OHs, as we rotate them from the top to the bottom, will go from being back to being up in front. Right? And then the CH3 is back, so it's going to go up in front. Alright, so what is the relationship between these two? So they're not mirror images. Are they stereoisomers? Yep, they're stereoisomers that are not mirror images. These are diastereomers. Alright, what about the last pair? Okay, let's see if we rotate this one to make the carbon chain like here. I'll rotate it this way. That one's back. It's going to end up being up. So the CH3s are opposite. These are enantiomers. Alright. So sometimes to make them overlap, we might need to rotate around a bond or just flip the whole molecule over. If you have challenges with visualizing these, sometimes it helps to build a model of the molecule and then rotate it and see what it looks from the other side and practice drawing it that way. Alright, so in the next video, what we're going to talk about is how we might analyze chiral molecules.